What is a DB? That is a topic for today's show. Hello, I'm Brady Volpe, founder of Nimbleness in the Volpe firm. This is a new series on RF and cable basics. Our guest today is Ron Hranac. Ron is a 50-year veteran of the cable industry who has worked for cable operators and vendors during his career. He's a fellow member of the SCTE and co-founder of assistant and board member of the organization's Rocky Mountain chapter. Ron was inducted into the Society's Hall of Fame in 2010 and is co-recipient of the Chairman's Award and SCTE Member of the Year, and is a member of the Cable TV Pioneers Class of 1997. He received the Society's Excellence in Standards Award at Cable Tech Expo 2016. He was recipient of the European Societies for Broadband Professionals 2016 Tom Hall Award for Outstanding Services to Broadband Engineering, and was named winner of the 2017 David Hall Award for Best Presentation. He's published hundreds of articles and papers and has been a speaker at numerous international, regional, and local conferences and seminars. And it doesn't stop there. Ron continues to contribute at Cable Labs and SCTE working groups, which I have the privilege to work with Ron, and we have a lot of fun doing so and get some work done too. Ron, thanks for joining our show today. How are you, and where are you broadcasting from?
Well, you're welcome, Brady, and thank you for the invitation to be a presenter on today's show. I'm in my home office in Denver's southern suburbs, getting ready for another winter storm to hit the area this coming weekend, but I plan on staying inside where it's nice and toasty. So looking forward to talking about some of the basics of this crazy industry we call cable. And we'll focus today, as you noted, on the decibel, or as I like to say, dB or not dB. That is the question. With apology to folks who are much more serious than I am.
Excellent. So I'm delighted that we're going to be discussing decibels or dBs today. And to kick off the conversation, I wanted to share an experience that I had when I interviewed by the first company I looked at. It was a radar manufacturing company. And I was interviewed by a very intimidating RF engineer that asked me the question, what is a dB? And despite just having graduated with a 4-year undergraduate degree, my answer was far from what was satisfactory by this guy. So that kind of proves that even with a degree, there are certain skills and knowledge that are learned on a job, such as understanding what a dB is, how to apply it, and things like that. So, Ron, with that, can you explain to me and our listeners what is a DB?
I am going to do that. I've got a little bit of a story to share too. I started in the cable industry back in 1972, and when I worked in the field, I had a signal level meter like a lot of folks out in the field do. Of course, I knew it was supposed to be used to measure signal level. It wasn't really clear to me exactly what was going on behind the scenes or under the hood with what this strange thing called DBMV was all about. But in I don't know, was it mid to probably the later part of the 70s, when I was still with Teleprompter, they arranged a training seminar that was put on by Len Ecker from Gerald. And old timers in the industry will remember the name Len Ecker. He was certainly one of my mentors and one of the technical pioneers of cable. But that's where I really learned a lot more about the decibel and the basics of signal level measurements and so on, because he was a real stickler about getting it right. And I think some of that rubbed off on me because I probably have a little bit of his attitude on let's make sure we get this stuff right. So I've got a presentation on the basics of the decibel, and let me hit share screen and we'll get this thing going here.
Outstanding.
And I have this, and let me put this in slideshow mode. And
Great.
I'll go ahead
We
and
can see your
hide the
screen,
little
Ron.
box here. All right, is it all ready to go on your end?
It does. It looks great.
All right. Well, as you can see, there's a lot of math on this slide, and I'm not going to talk about that math, at least not to that extent. Instead, this presentation focuses on the decibel, a primer. And of course, you see a tech squatted down by a pedestal in the photo there doing some signal level measurements or some kind of measurements. But to really understand what it is when we're measuring signal level and doing so much more in the cable industry, it really helps to have an understanding of just what the heck is a decibel and how does it apply to a lot of what we do in cable. Well, before digging into the nuts and bolts of the decibel, I think it's important to understand that decibels start with logarithms. You say, well, all right, well, what the heck is a logarithm? It's a term that's abbreviated log or log, but think of it as a shorthand way to represent really big or really small numbers. Now, take a look at the numbers in the table on this slide. And I've got four different numbers here, and I want you to think about different ways we can express them. So the numbers are 100, 1,000, 10,000, and 0.001, or 1/1000th. And there are different ways, a whole bunch more ways than I show in the table to represent these numbers. But as an example, the number 100 can be represented as 10 times 10. Or looking over in that third column of the table, 10 raised to the second power, or 10 squared. The number 1,000 can be represented as 10 times 10 times 10, pretty straightforward, or 10 to the third power. 10,000 can be represented as 10 times 10 times 10 times 10, or 10 to the fourth power. And then look at that number 0.001. We can represent that as 1 divided by 10 times 10 times 10, or 10 raised to the minus 3 power. That might seem a little odd, but it is a legitimate way to do that. So as you think about what I just showed you, what do those numbers have in common? And the answer is each one of them can be represented as the number 10 raised to some power. And what does all that mean? Well, the base 10 exponent, that is the power to which 10 is raised, is the logarithm. So if you look at 10 to the second power as being a way to represent the number 100, the little 2 that is the exponent there is the logarithm. So looking at this another way, here's a little tiny bit of math. The base 10 logarithm of 100 is 2. In other words, 10 to the second power is 100. The base 10 logarithm of 1,000 is 3. Or, in other words, 10 raised to the third power equals 1,000. The base 10 logarithm of 10,000 is 4, or, yes, 10 raised to the fourth power equals 10,000. And then we look at that 0.001, take the base 10 logarithm of that number equals minus 3, or 10 raised to the minus 3 power equals 0.001. And you can get the logarithm of pretty much any number if you have a scientific calculator that has a log button on it. So you push that base 10 logarithm button and you'll get the answer. So what that suggests then is that you can represent pretty much any number logarithmically. So let's take the base 10 logarithm of 523. And for that, we get 2.7185. And say, what? What does that mean? Well, it simply means 10 raised to the, 2.7185 power equals 523. So those are logarithms. Now that we have that down, and just keep that in mind as a foundation, because logarithms are an important part of understanding this thing we call the decibel.
And just a quick question on the logs there. So I saw you taking logarithms of small numbers, but taking a logarithm of 0 can be problematic, or taking a logarithm of negative numbers can be problematic. Is that correct?
Well, there can be some interesting things that happen when you push the logarithm button. And what I would do, or what I would suggest, is play around with the scientific calculator if you have one, and enter a number and then push the logarithm button and see what happens.
Perfect. And Ron, just before we get into the DB, we do have a question in our chat here. So Hank Yan, and I hope I'm pronouncing it right, Hank Yan, asks, does signal slow down when changed to a different cable with a lower VOP, or velocity of propagation? And would that create a sort of a signal traffic jam? So Ron, I know you're very familiar with this topic, and it's not really related to Well, it can be in dBs, um, but I'd
It's
like
a,
to I'd like you to maybe help answer this question.
well, it's a good question, and I'll go ahead and tackle that before we get into the fundamentals of the decibel. Velocity of propagation is an expression in percent of the speed of an electromagnetic signal through some medium. So in the case of coaxial cable, the RF signals passing through that coaxial cable travel at a velocity that is less than the speed of light in a vacuum. And we state that as a percentage. So, for example, a common velocity of propagation for hardline coaxial cable used out on the utility poles and under the ground is 87%. What that means is the RF signals traveling through that coaxial cable are zipping along at 87% of the free space value of the speed of light. In other words, the 87% of the speed of light in a vacuum. Now that's still really, really fast. And if you want to put that in to a different perspective, light traveling in a vacuum travels 1 foot in 1.02 nanosecond, or just a smidgen over a billionth of a second.
That's
In,
fast.
coax- in coaxial cable, with a velocity of propagation of 87%, the RF zips through that cable in 1.17 nanosecond. It's still just a little over a billionth of a second, but you notice it's slightly slower. A subscriber drop cable has a typically a little bit slower velocity propagation or lower velocity propagation, usually somewhere around 85% or so. So a couple percent different than or lower than the hardline cable. There is no traffic jam because everything is zipping along at the same velocity. So the signals traveling through hardline coaxial cable are they're all traveling through that cable at the same speed. Now, there's an interesting little thing that comes into play here that can cause a little bit of a monkey wrench to be thrown into the works, if you will. When group delay distortion exists, some signals are traveling at different velocities than other signals. So if you have a piece of coax, all signals travel through that piece of coax at the same speed. But if there's some impairment that would cause group delay distortion, then some frequencies may travel at a different speed or slower speed than other signals do. But that's a topic for another day. But anyway, no, it doesn't result in a traffic jam or things backing up or causing a mess. There's no issue with that because there's still, even though the velocity of propagation might be slightly different for drop cable than it is for hardline cable. No, that's not enough to cause any issues. They're still moving along at a rapid clip.
Awesome
Hopefully
answer,
that
Ron.
answers this
Thank you
question.
so much.
You're welcome. All right. So let's get into the decibel then. We've got logarithms as the foundation. So think of building a house of cable mathematics that includes a whole lot of things. The foundation is logarithms. And now we're going to start to build some walls around that house. And that takes us to the decibel. Decibel is abbreviated with a small or lowercase d and an uppercase b. And decibels, by definition, express a logarithmic ratio of two power levels. And there's the formula. dB equals 10 times the base 10 logarithm of power level number 1 divided by power level number 2. And this is true no matter what. We can derive a lot of things from this, but this is the basis of the decibel. So let's go through an example to show how we can put this to work. Let's say you have a 50-watt stereo in your family room, and your next door neighbor has a 100-watt stereo in her family room. How much more powerful is your neighbor's stereo than yours? And we can use the formula up above to figure that out. So we're going to take the 100-watt stereo that belongs to your neighbor, plug that into the numerator of our equation, and your 50-watt stereo goes into the denominator. So we have 10 times the base 10 logarithm of P1, which in this case is 100 watts, divided by P2, which is 50 watts. So we'll start solving this equation, and it is pretty simple. 100 divided by 50 equals 2. So next what we want to do is take the base 10 logarithm of the number 2. And the answer to that is 0.301. In other words, 10 raised to the 0.301 power equals 2. Now we multiply 0.301 by 10, and the answer we get is about 3 dB, actually 3.01, but about 3 dB higher power. So your neighbor's 100-watt stereo is about 3 dB more powerful than your 50-watt stereo.
So that's
Now,
that's not what you would really expect, right? It seems it's 100 watts is so much more powerful than 50 watts. And you're saying it's only 3 dB more or
it's only 3
3.01?
dB more. That's it. Now let's show. I know right where you're going, Brady, but let's show another example. Let's say a local FM radio station that serves your town installs a new 40,000-watt transmitter to replace an old 20,000-watt transmitter. So how much more powerful is the new transmitter than the old one in dB? All right, we'll do the same thing we did before. We're going to take 40,000 watts and plug that into as P1 and 20,000 watts as P2. Now 40,000 divided by 20,000 equals 2. And the base 10 logarithm of 2 is 0.301. We multiply that by 10. And the 40,000 watt transmitter is about 3 dB more powerful than the 20,000 watt transmitter.
That's
And right away,
shocking.
right, yeah,
Shocking.
yeah, right away you say, hey, how the heck can that be? Because in the first example, the power difference was 50 watts. The one stereo was 100 watts, the other one was 50. And in the second example, the power difference is 20,000 watts. So why does 3 dB apply to both examples? And here's the reason. The absolute difference between the power levels isn't what is important here or what matters. It's the ratio of the two power levels. In both of these examples, the ratio of the two power levels is 2. In other words, one power level is twice as much as the other. And that's a concept that sometimes can be a bit hard to grasp, but when you understand that the decibel is all about ratios, then all of this starts to make a whole lot more sense.
So before you go on, Ron, we have a comment from our friend Jason that I think really sums it up. He says, "What's the difference?"
What's the difference?
What's
And
the difference?
I think I know which Jason that might be. Yes, Dr. Dad joke, I suspect.
Yes, yes.
Uh-huh. All right. So what does this mean then? Well, by itself, the decibel cannot be used to express absolute signal levels. And this is a really important point to understand because there's a lot of shortcuts taken in the industry, particularly with regard to our lingo. For example, you can correctly say that an amplifier has 20 dB of gain or 30 dB of gain or whatever, or a splitter has 4 dB of insertion loss. You cannot correctly say, because it's wrong, that the input signal level to a cable modem is minus 2 dB, or the RF signal level at the output of a line extender amplifier is plus 48 dB. Those are both wrong. In order to express signal levels, the decibel has to be appended with a reference. And a good example of the one that we use in the industry is dBmV, or decibel millivolt. So in these two examples, the correct way to express them, that is the correct way to state the input to the cable modem, would be minus 2 dBmV, not minus 2 dB. Or the output of the line extender as plus 48 dBmV, not dB. Now, I'm going to give you a little hint of some things that will be discussed in more depth in a future technical session, because today I really want to focus on the decibel. And in another presentation that we'll do later on, we're going to talk about signal level. But it's important here to understand that dBmV expresses power in terms of voltage. And some people will say, well, that doesn't make any sense because the decibel has been appended in this example with millivolt dBmV, but it is power in terms of voltage, and here's why. 0 dBmV, which doesn't mean that there's no signal level, 0 dBmV defines the power produced when a voltage of 1 millivolt, root mean square, is applied across a defined impedance. And of course, in our cable networks, that impedance is 75 ohms. So what does that mean? 1 millivolt in the 75 ohm impedance is 13.33 nanowatts, or 13.33 billionths of a watt, which we call 0 dBmV.
Not much power.
Yeah, that's not much power, but it is power nonetheless. And remember our relationship before that we talked about. If you double a power level, the signal level goes up by 3 dB. So if you have 13, let's just round it down for simple discussion here. 13 nanowatts equals 0 dBmV. How many nanowatts equals 3 dBmV?
Well,
And
that
the
would
answer
be
would, yeah,
twice as much, right?
be twice as much, or about 26 nanowatts would be 3 dBmV. So that's how it works. And if you go the other way and divide by 2, if you go from 0 dBmV to minus 3 dBmV, what does that do to our power in watts? Well, it goes to about what, six and a half,
6.5, yeah,
six and a
half
half,
as
little over
much.
6.5 nanowatts. So we're cutting the power in half. Now, if we talk about other signal levels in dBmV, this gets back to the ratio piece of this. Those other signal levels in dBmV are technically ratios of those levels voltages relative to the 0 dBmV 1 millivolt reference. And there's the math behind it. It's level in millivolts divided by 1 millivolt. We take the base 10 logarithm, and in this case, because we're talking about dBmV, it's 20 times the base 10 logarithm. And the reason why it's 20 instead of 10 is something we can talk about in another session in the future, because there is a little bit of math involved about why we go from 10 times the base 10 logarithm to 20 times the base 10 logarithm. But in this case, we have to ensure that when we're talking about those signal level voltages, that we're talking about everything is in the same impedance. In other words, 75 ohms in our cable networks.
And that's an important thing because there are other, I mean, I think the cable industry, we do everything in 75 ohms, but there are other industries that use 50 ohms. So 75 ohms is pretty unique to our industry.
Yeah, and it's also been used, 75 ohms has also been used in broadcasting, particularly in baseband video. So a lot of the baseband video, especially in the old analog days, they use 75 ohm coaxial cable and whatnot in studios and so forth.
Yes.
So let's look at the correct use of the correct usage of the decibel. And this table shows different ways you can use dB in the left-hand column. So you can use dB to express gain, for instance, the gain of a drop amp or a line extender or trunk amplifier. You can use dB to express loss or attenuation. That would be loss through an attenuator, or loss through a splitter, or loss through a length of coaxial cable. We can use the decibel to describe signal to noise ratio, or carrier to noise ratio, or modulation error ratio, which is more accurately in most cases receive modulation error ratio, or RxMER. Return loss, which is not the same thing as attenuation in the upstream spectrum. Return loss is a way we characterize the impedance of devices and things. Noise power ratio is another metric that uses the decibel. Excuse me. And carrier to distortion ratios, for instance, composite triple beat, composite second order distortion, common path distortion, and so on. And in dBmV, the only thing we can use that for is signal level, or RF power. And I've got a big red X by all the others. We don't use the dBmV for loss, SNR, carrier to noise ratio, MER, return loss, or anything else. Now, I put an asterisk on dBmV because we in the cable industry have used dBmV for a long, long time. But there are other absolute values for measuring certain things. For example, in Europe, it's common to use the decibel microvolt rather than the decibel millivolt, but it's a way to express signal levels. The decibel milliwatt, we see that, or dBm, commonly used in optical fiber. That's also used in RF applications, but we probably see it more in optical fiber links and so on. The decibel watt, or dBW, is another way to express absolute values. The decibel volt, and decibel microvolt per meter, which is a way to express field strength. So if you want to learn a little bit more about the decibel, I would encourage you to check out an article I wrote called The Wise and Mighty Decibel, which appeared in an issue of Broadband Library. And there's a link on the slide to that article. There's a whole bunch of other articles that I've written in there, and I know, Brady, you've also written a lot of articles for Broadband Library, so a lot of really good technical reference information there.
And I think this is a great table that you put together because probably something I see that happens so often is people interchangeably use dB and dBmV or dB microvolts when, they should be using dB instead of dBmV and vice versa. So nice
Yes,
table, Ron.
we see that a lot, and I've got a couple examples coming up that will highlight that. So let me ask the group this: is this statement correct? The signal level at the cable modem input increased by 2 dBmV, going from plus 3 dBmV to plus 5 dBmV. Is this correct or not?
I'm going to say no.
And you're absolutely right. It is incorrect. Why? Because signal levels in dBmV cannot increase in increments of dBmV, only in increments of dB. So here's the correct way to state that. The signal level at the cable modem input increased by 2 dB, going from plus 3 dBmV to plus 5 dBmV. And the same thing going the other way, loss and so on would apply. So here's another example. Let's say you hook up your meter to the output of a line extender and you find that channel 2 signal level is 40 dBmV and channel 117's signal level is 48 dBmV. Is the tilt 8 dBmV or 8 dB?
Well, based on everything you've taught me so far, I'm going to go with 8 dB.
And you're absolutely right, because the difference between 48 dBmV and 40 dBmV is 8 dB. It is not 8 dBmV, it is 8 dB. So here's the last point to remember on this. Changes in decibel related values are done by adding or subtracting dB, not dBmV. And that takes me to the question slide. So I'll go ahead and stop sharing.
Outstanding, Rod. That was, I didn't really appreciate. I know you said you wanted to include logs as part of this in the DB discussion, and I think that was really important aspect of building up to the decibel aspect of this presentation. One thing I'd ask you about. So you talked about log base 10. What about log base 2? Why do we use log base 10 and not log base 2?
In the case of what we're dealing with in the world of the decibel, it is a base 10 logarithm. And this goes back to a bit of history. And this is my recollection from reading about this, I don't know, 30, 40 years ago, that the concept of the decibel came from the telephone company. And they found probably a century ago or so that a given length of phone wire caused a power reduction in the signals going through that phone wire. It always caused the same amount of power reduction. So they named that the bell in honor of Alexander Graham Bell. But like some other metrics like the farad or Henry used in capacitance and inductance, the bell is simply too big and cumbersome to deal with. So they chopped it up and divided by 10 to give us the decibel. And when you start crunching the numbers, then you find out that the relationship of two power levels, like I showed you in the formula, is a base 10 logarithm relationship. Yes, there are other logarithm bases. There's a natural logarithm, there's base 2 logarithms, and other bases. Base 2 logarithms we tend to find more in data communications rather than our world of RF. But yes, there are other bases for logarithms. It's just that what we're dealing with happens to be base 10. And think of it again as that logarithm is the number or the exponent to which the number 10 is raised to get some kind of number.
Awesome. And I know the focus today was on DB. We talked a little bit about dBmV. I think the next session that we talk about getting more into the signal levels where we can focus on that. I think that's really going to be helpful, kind of building on our education. So we're talking about that in about a month's time frame.
Sure.
For our listeners. That'll be a very nice thing to get into.
Yes, the signal level is it's an interesting topic, and we can get as deep into that as as you want or not, because that can really do a nosedive into the details of what the heck all that means and where it comes from. So yes, we'll talk about at least some of the fundamentals of signal level and signal level measurements in our next session. I think that will provide some informative information for the viewers. But an important point to understand, of course, is that the signal levels that we deal with in our cable networks are based on the decibel. So remember, the logarithms are the foundation of the house, the walls of the house are the decibel, and then we're going to start building rooms in that house. And one of those rooms is signal level. And there's a whole bunch of other things that use the decibel out there. We've used them, in leakage and all the things that I've talked about so far. But signal level is a biggie because that is such an important metric that we have to look at to ensure correct operation of our cable networks.
Excellent. So we didn't get any other questions that came in, Ron. Is there anything you want to promote that's coming up, papers, anything like that?
Well, I'll plug one thing. Some people like to dig into the mathematics of the cable industry. And for those of you who are interested in learning more about the math or having a good resource about the mathematics of cable, particularly if you're, say, a trainer in the company where you work, SCTE at www.scte.org has a standards download page. Go track down on the standards download page a document that's titled SCTE 270 2021 R1. It's called the Mathematics of Cable. That's an operational practice that was put together by an SCTE working group that I chair. When we started on that, we thought, well, maybe we'll have 50 pages or so of mathematical formulas and examples of how to use them, maybe 100 pages. The document came in at 425 pages. So there's a lot of good reference material there, and it covers the vast majority of mathematics used in the cable industry. Could we add more? Oh, I'm sure we could. But that's a great reference, and I would encourage folks who have an interest in the mathematics of cable to download that document. It's free, and it has a lot of great information in it. And I think of particular importance, the formulas, what they're used for, and then examples of how to use those formulas.
Great. Thanks for the information, Ron. And Ron, thank you for the great information today. Everyone, for our listeners, please subscribe, give us a thumbs up button if you like the information. We will be back ideally in a month to talk more about signal levels and continue to build on this, basic cable RF fundamentals. If you have any follow-up questions, please drop them in the chat below, and we'll discuss them in a following session or follow-up video. We will be back in 2 weeks to talk about how P&M is evolving in the industry with two great guests, Larry Wolcott from Comcast and Jason Roop from Cable Labs. Jason's also in the chat and been giving us some good jokes along the way. So thanks for watching, everyone. Ron, thank you again. Take care.
You're welcome, Brady, and thanks for having me. Take care, everybody, and have a wonderful weekend.